Good morning, guys. How are you? And welcome back to chapter 3. And this chapter is all about data and statistics, uh, brief reviews of main concepts, plus some of the things that will help us a lot in the next chapters where we talk about machine learning. As you can see, this is a little bit of a lengthy chapter, so hopefully we'll talk through it. The good news is you can always pause the recording, right? So I would suggest I don't know, maybe having like 15 minutes, 20 minutes, and then take a short break and come back. This always works out best for me. So today's chapter quote is the following. And data have no meaning in themselves. They're meaningful only in relation to a conceptual model of the phenomenon studied. You can find this in Professor Box's book, and I think this is the 1978 edition because I know later editions didn't have this, I think for some reason. This was under page 291. Yes, 291, the very beginning of chapter 9. I think it's empirical modeling, the chapter was called. But this is interesting because if you think about data, as you'll see in this chapter, if we're thinking about numbers or numerics, it's just, values, 1, half, 0, 15. And without having, let's say, units or stories behind them, it just becomes data. And this is one way to look at machine learning because the algorithms themselves, they don't really, most of them don't understand the concept of units or physics and stuff. So to them, it's just numbers. And when you build something like this on numbers, and then you try to come up and predict something new, it becomes a little bit, you know, I don't want to say hectic or concerning, but it becomes a little bit vague of how can a model predict things so well, but it doesn't really understand much of going on behind the physics behind it. So we went through this definition last time, and data is, you can think of it as pieces or information, facts, quantity, statistics. They're trying to serve a purpose for a reference or analysis. So to simplify, you can always think of data as information. And because machine learning has a big component of data, then it becomes a big component of information as well. When we think about data, we can think about two things. We can think about things that could label, like a unit. So we have it to label things. Or we also have it as something that's the main component, the value, the category, the class. So if we think about numerical, we have numbers and numerics. If we think about categories, we have classes. We also have different types of data. We have footage, audio data, video tape data, text data, many, many different types of data. Let's say if you're thinking about something with hydrology, transportation, anything with time, you're going to have a lot of time series data. So we can use data to do a few things. We can describe something, we can predict something, or we can try to understand something. Description is actually very simple. This could be level 1. We're building 20 beams, and we're trying to say that these beams have been casted. We have 20 of them. Some of them fail on this, some of them fail like this, some of them crack, not crack, and so on. We could also use the same data from those beams and create a model that can help us predict what would happen to a new beam that has similar features to those beams. This is basically supervised learning. We have the inputs, we have the output, everything is labeled. We can also try to create a model that we try to understand what's going on with these beams. For instance, like why this beam, or why beams A and B failed in flexure, beam C failed in shear, and so on. So you can see the different levels, and for each level, we're going to have to think about a process to analyze its data, collect/analyze this data. So the bottom line is we have this data and we're trying to come up with something for like we're trying to get some knowledge out of it. And whenever you start to combine different terminologies and domains, we're gonna have to think, okay, do we have now a methodology? Do we have an approach to do the following? And this is where things come down a little bit to data science. So data science, of course, in one of its definition is it's a subject that uses scientific methods, processes, algorithms, systems, procedures to extract knowledge from data. And funny enough, data is information and it has many properties, different types of properties, scale, size, types, rate of generation slash recording, meaningfulness, degree of confidence. You can think of many other things. These are the top five on, if they had in my mind while I'm doing this recording. And if you think also, if you like to visualize things, this would be like a very nice thing to visualize. You can draw a line here. So we can have numerical data, categorical data. If the data doesn't have an order, then this would be what we call nominal data. If it has an order, this is what we call ordinal data. So the way I remember these is order, ordinal. When we think about numerics or numbers, if we have a zero, it's part of interval. If it doesn't include, I'm sorry, if it doesn't include zeros, it's an interval type of data. If it includes zero, it's a ratio type of data. And we'll have examples on those very shortly. So numerical data, an easy way to remember them, they're quantitative and they're measurable. Think of force, weight, deformation, age. Sometimes this data can be discrete, exact, or whole numbers. Sometimes it can be continuous numbers. For instance, 1, 2, 3, 4 point something kilonewton or megapascal. Now, continuous data could also have intervals, so it has a scale. They could also be a ratio. They have zero values. Overall, numerical data are data that we can average, subtract, divide, do some mathematical procedures with it. Moving on. Yeah, this is one of the exercises I'd like to do. Let's do the following. So we have, you can actually pause this recording and just read these out loud. 33, 35, 48, 86, 88, 91, 97. They're just numbers, right? Now, what's the story behind these numbers? Well, the story, let's say we add some form of unit. Let's make them add a megapascal. So basically, we have these as somebody would say strength, concrete strength. So when you're thinking about strength, this now makes a little bit sense. So this is 33 megapascal. This is 91 megapascal. If you're like doing a lot of anything with concrete, usually 50, 55 is the cutoff between high strength and normal strength concrete. So now we start saying, okay, when we have a few specimens, maybe a few cylinders, and we've tested these, we have a bunch of them that are normal strength and a bunch of them that are high strength. We're going to come back to this example in soon, but try to link the megapascal to the numbers and the concept that we have normal strength and high strength, or the concept of passive. Well, this is how we move between different types of data. So for categorical data, well, they're non-numerical. So they have labels. For instance, low-rise, high-rise, autonomous vehicles, non-autonomous vehicles, shear, flexure, bending, cracking, creep, all these things could fall into classes. So we have them in, they could be nominal, they could be ordinal. Ordinal is something with order, something with scale. Minor damage, major damage, war, art. Nominal, it doesn't really have a scale, so it could be, fall under names or titles. For instance, different colors, red, yellow, that would fall under nominal. Sometimes in surveys we use these, but also in surveys, questions could be ranked. So it could have, 1, 2, 3, 4. So if you have a scale, it's a little bit different. Of course, footage data, this is what we're using like in computer vision models. For instance, yeah, this is another nice example. I actually Googled this because I wanted to be like to have very like a perception of how wide roadway network can be. So Michigan has about 120,000, 120,000 miles. I don't have my contacts today. I'm sorry, my lenses of paved roadways. Now imagine that you would like to inspect these roadways and figure out maybe we have some pavement cracking or some pavement issues with them. One way to do it is we could, have our state pavement engineers, so, drive around and manually check, uh, manually check for cracks. So we could manually check for these. We could also attach cameras to some cars, and instead of the engineers manually inspecting these, the cars would drive, and we take, videos and images of stuff. We could also have autonomous vehicles drive around with cameras, and then we can collect this data, and we could go back and we're going to ask the engineers, well, why don't you go through these footage? And whenever you see something, you link it. As you can see, this is going to be a very massive project. And because it has a big routine component, we could automate it. And this way we could build an algorithm that goes through the footage for us and does the labeling for us. And you can also see that there are different ways and things to do this process. So although we have different means, the core is the following footage. We have footage data that we have to go through and analyze. And if you can automate this process, great, because we can, and that'll be a very fun exercise to do. We also have other types of data, audio data, text data, and so on and so forth. So going back to, can we jump in or change one type of data to the other? Well, remember the example we did with the concrete strength? Now somebody would say, you know what, why don't we draw a line here? And let's say anything, above 50 MBA is, high strength, anything lower than that is low strength. So this way, all of these are high strength, and the opposite would be low strength. So this is how we can go from numerical to categorical. We can also do the opposite. We can say, well, these are now normal strength. Let's bring them back to high strength. I mean, to numerical data. Somebody will say, well, why do we need this? Well, that's interesting. It's a very good question. Well, we need it because sometimes, depending on the problem, we may not actually need to figure out the exact strength of this. All what we need is knowing if this is going to be normal strength or high strength. Another way is if you think about damage, let's say insurance purposes, we need to figure out first if this building is severely damaged or if it's doesn't have as much damage. So we can go back and reassess and maybe try to figure out residual capacity and so on. But from the context of this chapter, I think what I had in mind is the following. This is what we call specimen 1, specimen 2, specimen 3. These are the features of specimen 1, specimen 2, specimen 3. So the rows are samples, the columns are parameters or features. And as you can see, one sample here, sample 1 or specimen 1, it can have different features. This is a beam, high strength concrete. No, this is going to be its moment capacity. Does it fit or doesn't fit? So one specimen could have multiple features. You see this a lot. And each feature could be numerical or categorical. So what I'm trying to say is not all features have to be the same type of data, and not all specimens or rows have to have one single type of data as well. And whenever you start to think about this becomes a little bit interesting because usually we like to keep things consistent. But real life is not really doesn't mean not allow us to have consistent, stuff all the time. So what we end up with is something like this table, and we're gonna have to create a model. Then the question becomes, well, how do you combine different types of data to create a model? Well, this is where machine learning is going to be interesting. So once you start to collect data, let's say different beams, cars, highways, I don't know, sites, and stuff, we come up with a data set because a data set is a collection of data points. And a data set, this when we think about our area, we would like it to be healthy and balanced. And I know that these terms are don't really show us a lot of details and numbers because it's really hard to say, well, I need this many data points to come up with this data set that I can use to train model X and predict Y. But there's going to be a lot of engineering judgment here. And I think the point of this slide is to build up that judgment first before we start to put numbers. So something like the following, if you really think about the problem, we have to have a data set that's going to be representative of what? Of the problem at hand. And for this, it would be beneficial for us if we can have a good set of data points, a good set of features. And let's go a little bit now in depth. If I have a data set that has varying types of geometry and material properties, then I'm covering a number of different conditions. Let's say a number of beams, not just shallow beams or deep beams, different sizes of beams, different material strength. If I'm collecting some data too, I would like to have tests from different eras, something in 2020, 2010s, 2000s, 19s, 80s, and so on and so forth. Different eras give us different data. I would like it to have, maybe from different groups, different labs, different countries, different societies and stuff. Diversify. It would be great to have like complete responses instead of saying that this beam fails at this load, load point. Can I also have, load deformation curves? Can I also have a description of boundary conditions of all those stuff? It would help to have a few duplications, not that much, just to make sure that some specimens were not like recorded by mistake or like they didn't have issues while recording them. Somebody like missed a digit here or there. So some duplications usually works or acts like a second degree of confidence, but not all the time. We have to be careful with duplicate specimens. And of course, everything we talk about has positives and negatives. For instance, one of the things somebody can think about is, well, when we're talking about this point, let's say collecting data from 20s, I don't know, 1990s, 80s, and so on. Well, if I'm trying to build a model for today's concrete, well, material that was in the 80s and 70s may not have good representation of the concrete we have now, which is a very valid point. Somebody would say, if I'm trying to build, I don't know, like a model for deep beams, for instance, why do I have to have shallow beams? This also makes a lot of sense. So the discussion here is really we're trying to tailor the data set to the problem at hand. And this is the emphasis. So sometimes we don't really have to go back 20 years ago or 30 years ago to get some data. We don't have to test or like find all different types of beams or all different types of vehicles or highways or bridges. It has to be tailored for the problem. And this is where we say, okay, if my focus is on, I don't know, specific type of structural members or systems, then I'm going to be trying to get as many variables or as good variety as I can for this particular set of parameters I have. Of course, if we're dealing with something else like with images or audio, we would like to have different textures, different colors, different quality, different orientations for cracks, different grayscales, and so on and so forth. And this is where we are building a data set. Now, once you have a data set, The first step is we're gonna have to go through it and see, okay, well, does it look okay? Do we have issues with the data set? Do we have any noise? Do we have any outliers? Do we have any missing data? Do we have any data recorded in error? And this is where diagnosing and handling comes in, because we're trying to filter our data set a little bit. Maybe there are some features that don't help us as much. Maybe some data points were done, very, very old. We don't need them. Maybe we have a lot of noise, a lot of outliers. We have to remove them, because if we keep them, well, the model is going to be learning on this data, and then it becomes a little bit hard for the model to distinguish which is good, which is not good to use. So qualitatively, we are looking for healthy data sets, healthy data that has or that can give us high quality information. So the emphasis is, in qualitatively, we feel good about this data set. When we look at this data, we're comfortable that it covers a lot of the things we're trying to do within our domain area. So let's say that you have some missing data. What do we do? Well, here is where usually we have questions. Well, why do we have data set? Or I'm sorry, why do we have some data? Well, the bottom line is really simple. Data can be missing to many, many reasons. If you would like to learn why the data is missing, that's a different field, actually. We're going to go through this once we go through the PDF. But for us, at this point in time, we know that some data is missing. So what do we do? Well, if a data is missing, you can take out that data point, delete it. Or you could fill the data or the missing data with some data. Well, so we could delete it or ignore this data. We could fill it with some data. Sometimes we can actually use ML to fill the data for us, which is, I'm not going to go through this now. Let's focus on one and two. Let's keep things a little bit simple. So if you delete something, it's easy. It's gone. It doesn't exist in the context of the data set. If we would like to fill it, well, we could do the following. We could take the average. Let's say we have just like our specimens, but you can take the average and fill that missing data point with the average point. Or we could interpolate between the two nearest points for the data point that's missing, and we take the interpolation of those points. For instance, let's say that in this case, this number here is this number here is missing 86. So if I substitute 86 with the average of the other 5 points, which is 68.28, the new average becomes 65. So the original average is 68, the new average is 65. So the average is not that far, but it's still high strength. It's very close. If I completely remove it, you're going to change the average, and then the new average will be a little bit different as well. The difference may not be that much. However, this is a very, very simple example. And you can see the data points here is actually not that far from each other. But if you have a large data set where you have values that are, I don't know, negative 300, 1400, the average will, might be different. If you have a very, very large data set, number-wise, removing a few points may not change the average as much. If you have a small data set, removing a point might change the average that much. Even substituting with a point might change it a lot. So here's where we're gonna have to think. Well, does removing one sample, serve our purpose or doesn't serve our purpose? So the more problems that you do, the easier it becomes to visualize, because sometimes removing a point may not be the best option, especially if you have a small data set or if the data is very expensive to collect or measure. Similarly, substituting might not work out because the point might be just so far from each other that the average would, may not work out. There are, of course, other ways that we can figure this item out, and I feel that might be a good discussion for a later turn. Let's not add too much into this item. Now, of course, we also have outliers, and outliers are rare. An exceptional data that do not conform to the norm. Well, let's say within a feature, for instance, we're thinking about the strength of concrete. All of a sudden you have a value of -2, or you have a value of, I don't know, 50,000. Well, it's going to be very, very hard to create concrete that has a 50,000, MPa strength. It would be great, but I don't know. It might take us some time to get there. Similarly, to have a negative strength may not be physically meaningful. So this is where we sometimes we're going to say, well, okay, well, this might be an outlier. Something is off with this value. It could have been recording by mistake. It could have been the equipment or like this wasn't measuring correctly, and hence we have this funny number. So an outlier is something like this. You have the data here, most of the data here, and you're gonna have one that will live it all the way somewhere else. Now the issues with outliers is they tend to shift the data or the average of the data. Sometimes we think they're correct values. Let's say that you have a value that's, I don't know, 20 MPa, and for us it may seem like a good strength because we do actually have 20 MPa strength, but if you look at the other features, there's something awfully wrong with this value because we might be using steel fibers or like different types of fibers. It could have been 200 MPa, UHPC, ultra high performance concrete, and yet we have a value of it as 20. So something might be off there. So once we clean the data a little bit, it's a good exercise to visualize the data. We would like to see how it looks like. And the goal really at this stage is to have an understanding of the data. And we were trying to see, can we see some trends? Can we figure out very, very rough idea about how our data distributions is? And distribution is a very key word because distributions is how the data is can be plotted. And this is where we're going to start to think about basic statistics, very, very basic stuff. And most of these things are known, actually. We've known this for a while because you've probably taken, a lot of, math courses and engineering courses and stuff. So we have range. Range shows the spread of data. What's the first point? What's the last point? We also have min and max, smallest value, largest value. We have the mean or the average, for instance, mean. We also think about the median. Median is the middle number of the data. Think about mode, most common or most frequent data point or value. If you have a symmetric distribution, these things tend to be aligned together. If you have a skewed distribution, they may not align. It's going to be unlikely for them to align. So knowing all these things becomes important. Now, if you have a lot of features that are symmetrically distributed, this is actually a good thing because most of our data is. Sometimes if we don't have like enough data or a good collection, we're going to end up with some skewed distribution. This is where things could affect our model a little bit. We also have skewness, kurtosis. So skewness is a degree of asymmetry when something is asymmetry. Kurtosis usually describes the tail of the data, like how far it is. And one fun fact, if you look at these equations, this is to the power. This is to the fourth power, third power. We also have second power. So it's like you're adding a power to it, and all of these things we have different, different limits for them. So skewness of more than 1 or less than 1 indicates high skewness. Kurtosis of more than 3 is usually different. If it's 3, it's about normal distribution. We also have weakness. We have a lot of ways that we can describe data. Now, some of the things that instead of describing the shape of the data, where we can describe the statistics of the data, is we have variance and standard deviation. The variance is the spread. It tells us how data points differ from the mean. Standard deviation shows the dispersion and how relative it is to the mean. So this is where the second degrees comes in. On average, how far each score lies from the mean. Now you'll see a lot of emphasis on the mean, and the emphasis on the mean is because as we will see, we have a tendency to like normal distributions. A lot of our phenomena, a lot of our parameters actually follow a normal distribution. Some of them, they may follow different types of distributions, central tendencies, as you know. So when we visualize the data by metrics or by statistics, we focus on these terms. And then when we focus on the data or try to visualize the data using like tools or, imagery, this is we're going to come in with something like, histograms. So histograms, they look like the following. And they show this distributions. They show, numerical features. They show the frequency of a feature. So for instance, if you have a feature that lies within this range, this is how many times we can see it. This is how many times we see this range. This is how many times we see this range. Histograms also show us if you can actually connect these, it shows you that we have, something like this. We can those skew show us whenever you have a skew, basically this one tells you, well, you have a lot of data here. You have a little bit of data there. So why is that? Is it possible that most of the tests you've collected tested specimens that have features within this range? Is it possible that you need to go back and collect data from specimens that have different features or in that range? Or which is actually more common than not. In this case, we're plotting tube thickness. So steel tubes are steel tubes like circular or could be like a rectangular or a squared steel thin members that sometimes we fill them with steel. We fill them with concrete. They could behave as columns. If most of the time we have specific thicknesses to these tubes, and this is why you see a lot of emphasis on the left side of the histogram. We don't really use tubes that are very thick and very expensive. This is why we don't have many tests that have this thick tubes, thick tubes. We also have box plots. This is how a box plot looks like. It shows us actually, for instance, in this case, shows the strength. It also shows us the mean. Mean is this little x. Median, those lines, IQR or interquartile ranges, these ones here, outliers, right there. It's a way to show us a little bit more information about the data we have. We also have scatter plots. These are much more common. You'll probably have done these in your construction lab or fluids lab. So these ones actually show the relationship between two features. In this case, axial capacity of columns versus the tube diameter. And if you look at these plots, you can see, oh, okay, so there's almost a linear relationship, which makes some sense. Larger tubes means they can have a little bit higher capacity. What also these plots can tell us, well, if you look here, you seem to have hopefully a lot of points in this case. You have a little bit of points there. Now, these could be outliers, but most likely than not, these are the types of data that you can get because you're testing very large tubes, which we don't really use much. Use them on all of it. And sometimes if you look at the plotting itself, so these are the same data between these two plots. Sometimes they just look a little bit better if you like fill the data with something instead of having blank. Right? This is another plot where it shows data that it looks, you can see there's a lot of data, but in reality, this shows data for different parameters. All of these are different parameters. So the way that to make the plot looks a little bit nicer is you could use different colors, different highlights, different labels for it too, so you can distinguish type of data. And this becomes handy whenever you have multiple parameters. Now, we also have visualization tools that can help us with categorical data or features. For instance, bar chart. And bar charts can be something that shows, we have buckling, we have crushing. This is how many short columns we have, how many long columns we have, how many very long columns we have. This shows count, and of course, this shows the ratio when you put everything together. So you would see out of everything we have here, about 10% is actually very, very long. About 40% is long columns. About 50% is, short columns that filled in buckling. And same thing for the other series. So once we start to visualize, it becomes easy to explore because now we have things plotted, and now we're going to try to explore the data or quantify some form of relationships. Do we have a linear relationship? Do we have a nonlinear relationship? What kind of relationships we have? And of course, the easiest thing for us, or the thing that always comes to mind, is correlation methods. Here is where we have the easiest thing, actually, linear relationship. And linear relationship, it's very easy to see. It's basically something that would look like this. You have data, and you have some form of like a straight line. It could be like this. It could also be like a negative relationship too, but the emphasis is on linear. Linear means somehow straight, somehow direct. And correlation base, the first thing is Pearson correlation coefficient. And as we know, it goes from -1 to 1. And this one shows two things. This one shows the strength. So the value is the strength. For instance, R of 1 is very, very strong. -1, very, very strong. 0.2, not that strong. And direction. So the signage is the direction. So +1 is a very strong positive correlation. -1, very strong negative correlation, and so on and so forth. However, this is where we have to pause a little bit. Whenever we think about the linear Pearson, this one emphasizes linear relationships. So everything is based on the linear relationship. So basically, you're plotting things, and you're assuming that the relationship is linear. And this is very important. In real life, the relationship may not be linear. So these values here is the strength and direction of the assumption of the linear relationship between them. Now, if the relationship is actually linear, great, perfect. But it doesn't mean that this causes this with high strength or like positive strength or something like that. No. It also it doesn't mean that the relationship is indeed linear, nor that there is a linear relationship. So we have to be careful with correlation. Now, when things are not very defined, we also have Spearman's correlation coefficient, and this one shows the monotonic relationship. For instance, this is a monotonic relationship. It also shows the strength and direction. However, just like in Pearson, this one implies that there is a monotonic relationship, but it doesn't have to. Like in reality, it doesn't have to mean that the relationship is monotonic. And if you can calculate the correlation for two parameters, you can do the same thing for many. And you're going to end up with this. This is the correlation matrix for Pearson. This is for Spearman for the same data. And you'll see something interesting. For instance, in this case, everything in the diagonal is 1 because the relationship between the parameter and itself is 1. But if you look here, the relationship between P and R is 0.41 linearly, or based on Pearson, it's 0.72 based on Spearman. So which one it is, right? Is it linear or is it monotonic? You can see many examples. For instance, in this case, this is a -0.16. This is 0.012. Now, both of these things are correct because both of them assume something about the data set, right? However, when we try to interpret this data or this information, we have to remember that we have to use the right terminology. So you can say this relationship is 0.012 based on the linear Pearson correlation. But again, that doesn't mean that in reality it is linear. We could also have them plotted like this, and instead of having them as values, sometimes this could be a little bit helpful. You can see, for instance, here, the relationship is oddly satisfying. We also have other types of methods. We have information-based method, for instance, mutual information. This one measures nonlinear relationship. So instead of measuring the linear relationship or the monotonic relationship, now we're doing nonlinear relationship. And this is where there's going to be a lot of information theory background there that you might want to like go back and read a little bit. But the things I would like to emphasize, this one tend to capture nonlinear relationships based on a simple thing. This one tells us the amount of information one variable reveals about the other variable. So if you know information about variable X, how much does it tell you about variable Z? This is the mutual information. Of course, its calculation is a little bit more complex than the traditional linear stuff. We have many other methods. We have trees, point by serial, more other methods. Some of them are for binary values or data. Some of them are for other types of data. This would be a good exercise to come up with to do something with Excel. So let me switch back to my Excel, and you can find this data set online. So let's clean this up a little bit. So what I'm trying to do here, I'm trying to show where I have the diameter for columns, tube thickness. Let me see, am I sharing the screen? Yeah. Effective length, yield strength of steel, compressive strength of concrete, axial capacity, failure mode, column type. For the times, for now, we can just hide these two columns because they're categorical. We can do the following, or actually, since we can do this. We can easily plot these two. So if you go to insert, then charts, and scatter, this is what we have. So tube thickness, we have the x's and we have the y. So this would be the tube thickness here in blue, and this would be the diameter. If you would like to add these, I'm sure you all know how to do this. This would be, for instance, this is the diameter. I'm sorry, this is thickness. This is going to be the thickness of the thickness in mm. And this would be the diameter as well. If you don't want to have these, you can remove it. If you would like to play with this, you can always go to format, markers. You can have them in different shapes, and you can fill them all or unfill them. You can change with color right from. So this is like a brief way to doing things in Excel. Now, if you would like to do some analysis, let's say we don't need this anymore. Some correlation analysis. So let's highlight these. Let's go to data. Let's go to data analysis. And then from here, you can do correlation. You can have histograms plotted. Let's see the histogram. So let's do this. Well, okay, I don't want to do the pin range like this. So let me just revert back to correlation. Let's have this all highlighted. Yes, I have labels in the first row. For the output, I would like everything to be right there. And you can click, and this is going to be the matrix for Pearson. Negatives and positives and all. There are some easy ways to make things look a little bit pretty, so you can always come here and you say, well, if it's greater than 0.8, I would like this to be in red. If it's between, I don't know, 0 and 0.2, I would like this to be, let's say yellow. And then you could do green, you could do blue, you could do all the elements. Spearman is a little bit tough with Excel. It doesn't have like, I don't think it has a very quick way to do it, but this is how we do correlation. If you would like to plot histograms, actually, let's go back to that one. You can always add them from here. So this would be the histogram. And we can always change this. And if you slide it over, you have it for different types of features. No, no, this is good. This is good. We also have reformatted visuals here. And they also have quick layouts. You can try this. I'm sure most of you are very familiar with this. So this is actually the example that we did step by step. You can have it. Okay. And this slide is what I would like you to start to think a little bit. So we have data. We've cleaned the data, plotted the data, visualized the data. We've seen some patterns. Now is what is a good time to start to think about, well, which out of all these features we have, do we need all of them? Or is it possible that some of them don't really add much? Is it possible that some of them, only a few of them actually have, if we use them, would give us the most amount of accuracy, for instance? And this is what we refer to feature selection. We are trying to select features to have, to help our models be a little bit, their performance be a little bit good. Now, when we do this, we're basically trying to do a few things implicitly. With ML, we're really trying to improve performance, and this means, for the most part, improve accuracy or prediction accuracy, because up to this point, we're thinking about accuracy. We're also trying to avoid overfitting. We're trying to have models that are fast, because if you think about it, instead of dealing with 50 features, if you're dealing with 10, the model will be faster, right? Cost effective. It doesn't have to go through multiple things. Also, for models with small features, it's easy to debug. Let's say if you have an error or if you have something that's funny, you can always revert back to the features, to the selected features, versus everything else. So what we normally do is you could start with one model and run all features, and then from there you can start to select features. You can compare both. That'll be a good exercise. And with features, there are with feature selection, there are many things that one can think about. One of the things I like to use a lot is I'm trying to use high merit features. High merit features mean features that can retain a lot of the information, but at the same time, I'm not losing accuracy, and I'm not trying to use any features. So it's a kind of a balance, and this is where things like outcome trees are becoming. You'll see it a lot in different sources, different books. In general, it says entity shouldn't be multiplied beyond necessity, which means the simplest form usually wins. Or the best explanations are the ones that involve the fewest possible assumptions. I think it's a good way to look at feature selection, but you also want to keep in mind that, let's say, if your problem have 4 features or 3 features, it may not be worth it to use one feature or two. It may be, it may not. But if you have like something humongous data set, then it actually could be helpful to try to reduce this number of features. It's very problem dependent, so we have to be careful with that. We have to be careful with that. So how do we, explore this? Well, we have methods. We have different types of methods. We have filter methods, wrapper methods, and embedded methods. Filter methods, from their name, you're trying to filter features. And most of the time, these happen before the analysis. So for instance, we're thinking about, beams or air quality or water quality. We know that certain things don't really affect the analysis that much. So if you think about, I don't know, steel beams, well, the concrete type is not going to affect the steel beams because they're made from steel. We can't really use concrete, so we can eliminate the feature for concrete with high confidence. We could also use some statistics. We could use some statistical analysis to identify the high important features and remove the other features. However, just like everything else, we have to remember things. When we use statistics, these methods, they apply some assumptions. So basically, you're saying, well, I'm removing this feature because the method I'm using is assuming that this feature doesn't work out as much based on the assumption of X, Y, Z, not based on the thing that you have in mind, not based on physics. When you're using domain knowledge, you're also doing the same thing. You're basically saying, well, I know from my experience that this feature doesn't work out or it doesn't affect as much. I don't need it that much. This could be labeled as like your opinion. Another engineer may not agree with you, right? So we have to be careful with those things. We also have, filter methods. They have advantages. They're usually very, very simple. They're usually efficient, easy to run. That's what efficient means. They are independent of the analysis, so they don't really rely on a specific algorithm. They're just methods. We use them once. That's it. They're really good at finding trends. And trend is global things that are in general. However, of course, everything has two faces. They disregard mutual dependency and interaction. For instance, when you say that concrete doesn't really, or strength of concrete doesn't really affect the strength of steel as much, right? Well, this could be true if the output doesn't have concrete in it. For instance, if you're thinking about concrete filled steel tubes, we have steel columns that have concrete and steel, then there is a relationship between those two. Filter methods tend to ignore this relationship, whether with the target or with other features. If you're thinking about the steel beam and you have, let's say, this beam is between concrete walls or shear walls, well, the strength of the walls affect the strength of the beam because it's in fixed conditions. So there is some dependency between the strength and the member, or between the two features. So we have to realize that. So we have to be careful. Route methods are a little bit different. Wrappers, what they do is they just compare all combination of features to identify the combination of features that would give you the best performance, aka accuracy of the model. So what they do is we have metrics. This could be, for instance, R squared, and we try different combinations until we realize that when this combination or this feature, if we use it, it tend to increase our error. If it increases error, then it's not, it doesn't help us with the performance of the model, so we remove it there. As you can see, the emphasis here is on accuracy. Actually, thinking about this, maybe R squared is not really that a good correct metric. Maybe something like mean average error, because the error here increases. When the error increases, we terminate the analysis. So whenever the error increases, that's not good. For R squared, actually, this would be good because we're increasing R squared. So that might not have been the best example. This would be a much better example. So the focus is on accuracy. And because our focus is on accuracy, remember, this becomes a prediction problem. And we don't really focus much on the causes of physics behind the problem. There's a difference between prediction versus understanding. Embedded are methods that are used within the algorithm. So within the algorithm, they have different implementations. For instance, they have regularizers or constraints or objective functions, and the method try to manipulate these and try the different um, I don't want to say details, but try different organizations or different characteristics of these constraints to improve its own accuracy. Now, if you think about this, this would be something that we actually might label as something that's good because everything is done internally within the model, right? However, the opposite coin would be the following. Because everything is about the model, this is where we're gonna have to have some algorithmic bias because now the model is figuring out this works its best, the best for this particular model, not for other models. So if you compare different models, you'll have different performances. Yeah, you're gonna have to balance what you know. How do you go from there? So that was feature selection. Then we also have feature engineering. Feature engineering is, you can think of it like this. Feature selection, you're trying to select features. Feature engineering, you're out of the ones you selected or out of all the features, can I combine the features in a way that I'm gonna have a new feature? And this new feature is good because one, I'm dealing with one feature versus two or more features. And two, it's good to have because it combines a lot of information from different features. Now, this sounds great on paper. It is great on paper. However, we also have to remember that the new features could be numerically effective. However, they may not actually reflect anything on the physical problem. For instance, somebody would say, I'm going to use, I don't know, strength of concrete and strength of steel. I'm going to divide these, the F prime C over Fy as a new feature. Great. Another person would say, well, I'm going to go with Fy over F prime C as a new feature. This could also work out. The difference is you're going to have a ratio of more than one, most likely a ratio of less than one. Somebody would say, you know what? No, I'm going to go with something else. I'm going to go with the steel tube over strength of concrete. And numerically, you could do that. And this could actually give you some effectiveness too. But physically, what does this mean? What's the tube thickness over F prime C? If you look at the units, the units are all over the place, right? So it may not be physically correct. Now, here's where you have to pause and think. For some models, not all features have to represent physics. For some problems, we don't even know the physics of the problem, right? But for the problems that we do, having consistent features might be valuable. It doesn't have to be, but it could be valuable for some engineers. What I'm trying to show is I'm trying to show different types of views for ML, because I think at this point it's important to realize those. I don't think it's a good thing to focus on one way to look into things. I think the more information you have or the more perspective you have, it becomes a little bit easier to visualize and see, okay, well, this is why I can do this, and this is why I shouldn't do this. And it also becomes interesting to owners and let's say building officials because you're gonna have to explain these to them in the future. They're gonna ask for explanations. Uh, Another way that we can manipulate data is, for instance, scales and units. What we have, for instance, diameter is an mm, yield strength is an MPa. If you look at the numbers, this is 178, this is 44. So the numbers are different, massively different. The units are massively different. So what we do is it might be a good way to uniform things or to unify things. So maybe using one unit if possible, or using dimensionless analysis, or using one scale for the data. All of these things tend to affect models' performance a little bit. So one workaround is normalization. This is also called the scaling. I try to avoid using scaling actually. And I personally I avoid using scaling because standardization has an S in it, and sometimes I confuse both. Uh, So normalization is basically where you take the data point and you make it between 0 and 1. So it's like x minus x min over x max minus x min. Standardization is where you have where you center the data about 0 and you have a 1 unit of standard deviation. So x minus mean over standard deviation. All of these things are different methods. You could try both and compare your analysis. These tend to tame the data a little bit. We could also do some manipulation for categorical data, although a lot of the new algorithms do this by default, but the way it works is, let's say we have a data set where we have a feature that says freeway, highway, and expressway. How would the model understand these words, right? Well, what we can do is we can convert these into numbers. We would say freeway is 1, freeway is 0, highway is 1, and expressway is 2. So we're converting categorical into numerical. Data size, yeah. So usually the question is, what's the minimum size of data that we need? The question is not what's the maximum size of data. The minimum, there is a big research area about this that's trying to answer this, but I like to have these as so 10 per feature or 23 per feature, or the feature or the ratio between features to observation between 3 to 5 different researchers, of course. You can have it as the bare minimum, and always try to avoid using it. Always use more. That would be my suggestion. Yeah, at least for now. You know. Hopefully soon we'll know more about the minimums. Statistical concepts. So the last 10 slides are actually, or last 11 slides are all about statistics. As you know, statistics, their methods and procedures. We do have populations, and for populations, we have parameters. A population is like the general thing. A subpopulation is called a sample. And for a sample, we have a statistic. So P and P, population parameter, statistic, and sample, SNS. And for us, really, we're focusing a lot on central limit theorem whenever we have very, very large data. The mean can be approximated with a normal distribution. This is what we mean. And this is actually very good and very helpful for our case. Because once things start to move away from CLT, becomes a little complex. So we've seen deviation, we've seen variation, but I would like to reiterate here the following. So the variance describes the variability in terms of the squared deviation. The squared deviation means units squared, so strength squared or deformation squared sometimes doesn't make sense, right? So we use a standard deviation for we bring everything back. Now a distribution is a description of how often a numerical value occurs. This is a distribution. This is a normal distribution. We could also have, density plots where we describe the probability, and everything has going to be equal to unity. Regression. Regression is the thing that we probably remember the most from math as engineers, I guess. So we could use it to predict something or explain something. We could use it to characterize relationships, to determine the importance of relationships, to compare different dependent variables. And this is going to be interesting now. The simplest form, when we have, as we all know, we have many forms, but the simplest form is where we have some data and we try to fit a line. Something like this. We can have a slope. We're going to have intercept, and we will have some error. And we have x. X is, independent variable. Y is the dependent variable because it depends on x. In this case, you can see we only have an x, one variable. The slope goes with x. The intercept is free. So the intercept basically tells us this is if x is 0, it would be 0. y equals to the intercept with some error. Tells us that the intercept tells us the value of y when x is 0. The slope tells us how much, we're gonna have to change x in terms of y. So regression, or linear regression, have a number of assumptions. Most important ones are 5. The most important one also says the existence of a linear relationship. In real life, most of our relationships are not really linear. So we tend to violate this assumption. It's a problem. We also have other assumptions. Of course, we have there is a big discussion what to do if one assumption is violated and stuff. This is a good, you could go through these. I don't think this would be a good time to describe all of these things now because I think we're pushing more than that we need for this lecture or for this book for that matter. There'll be like a very good discussion for a statistics book. So I would advise it to go there. Maybe you could read Professor Box's book. We have a very good discussion there. Assumption 2, multivariate normality, and a linear combination. Remember how here it is. Linear combination of values should have a normal distribution. This could also be easily violated as well. No or little multicollinearity, independence, big one here. We tend to violate a lot of these things to different degrees. When the residuals there is consistent, we also have sometimes we do have issues with that. But the point is the following. The point is not that regression is bad. No, the point is whenever we use a regression-based method, we have to conform to its assumptions. When you're using linear regression, we have to make sure that we don't violate of as many of a lot of the stuff we have with regression, with linear assumptions. So just like other methods, regression has pros and cons. Machine learning has also pros and cons. And we have to remember that when we use something, we have to learn to appreciate its basic assumptions. For instance, something like this. A straight line is where we have an x. In this format, we have x. We also have x. We have x. So this is the same variable. The difference is this is squared. This is cubic, quadratic, and so on. And this is where we have polynomials. Then in this case, here's what we have. Now we have x1, we have x2, x3, we have different variables now, no longer x. This is where we have multiple linear regression, and the linearity is actually, this is linearity, is pluses. But in reality, we don't really know if the relationship is plus or not. This is why a lot of those things don't really work out as much for us. They do to a certain degree. In this case here, we have x1, we have x2, now we have x3 and x4. We had multiplication between variables. It's no longer linear. This is what we have a little bit of nonlinearity there. We still have the pluses. But we don't know if the relationship is there or not. And of course, all of these were, simple regression, multilinear regression, but in reality, we have much more in regression. We have non-parametric regression. This is where a lot of the assumptions we mentioned, we overcome them. We have logistic regression. So we use a lot of linear regression. We use a lot of linear regression. We use a lot of multilinear regression as well. And we use a lot of different forms of linear regression. But the issue is not really with regression. The issue is that we use something, but we don't really tend to use it, or at least knowingly tend to use it in the best way to describe it. We tend to assume a lot of things, which is fine for some, but as long as we know that we're assuming these and how they relate back to the main assumptions, we should be good to go. So the bottom line is the following: don't be afraid to use regression. Helpful. And we have to always remember that we have assumption that we have to go back to. Okay. So let me pause for now. I'll let me get my PDF ready and I'll get back. Okay, we'll come back. Yeah, perfect. So we're sharing the right PDF. As we've seen, we had a lot of discussions on data collections, handling manipulations, and so on and so forth. We've done those too. Yeah, this is a nice scene. It also meshes with the data-driven analysis. And if I theorize before you have data, invariably you end up trusting facts, so theories instead of theories, so facts. And this is actually very, very good when you think about data-driven analysis because we have the algorithm, and if the data changes, the predictions change, and there's going to be some kind of conflict between those. Now we've talked about description, predictions, understanding or causal understanding. We've talked about yep, all of this was fine. Regression, classification. So whenever we think about regression, we think about numericals and numerics. Classification, we think about classes. So depending on the data, we could do, and this is where you could start like a regression problem. And if you modify the output, let's say as we did with the specimen, with the Congress specimens, from strength to high strength or low strength or normal strength complete, we could change the problem from regression to classification. Sometimes could be needed. We've talked about the Michigan example, time series we did. We've covered those. Yeah, this paragraph is the one for the small, like how small we can go with the data. Hopefully this will change soon. Yep. Okay, so here. So we talked about how data can be missing, and I think there are many other ways that we can describe this. For instance, we have missing by design. This is when data is missing deliberately. For instance, we don't record something. Let's say this is a very small crack. We're not going to worry about it. Missing completely at random, or when data is missing due to random factors. Let's say something is lost, like the strain gauge is damaged or something. We have missing at random. When data is missing is not related to the missing data, but rather to the sum of the observed data. We don't report a crack because the specimen is not made from, let's say, made from steel instead of concrete. It doesn't really crack as concrete, so we don't record that. Missing at random when the probability of data being missed varies for reasons unknown to us. So there are like 4 or 5 things that would fall under how and why data is missing. Yeah, this is a very good book, by the way. Johnson's and Johnson's. If you're thinking about feature engineering, feature selection, they have very, very good examples. And it's online too. I think they have the free edition is online. We have those some functions for Excel, Python, or yeah, you could follow. Histograms, box plots. Yeah, we've done those. Yeah, this is I don't really hide this in my slide, but let's say you're trying to have histograms, and if you remember, if you go back to the presentation to the like to the same recording, to the Excel example, the first one I was trying to plot using plot histograms using the data tool, and there was like a little option for bands, and I didn't do anything, and I reverted back to the correlation. It's because of this. I wanted to talk about this first. So the size of the pen size is actually, I know Excel does it by default, but there is a lot of theory behind it. So for instance, there are many methods you could use this width of the pen. We have Sturgis and we have Scott's methods here that you could use to have a scientific way to actually present those pens. Because somebody's pen would be like a little bit different than the other ones, which is fine, but there is a way to properly do it, and that'll be here. There are a lot of packages that you can plot these on Python or to. All of this is fine. All of this is fine. Yeah, violin plots, funnel plots, series plots, different types of plots. Some of these figures can be, like, especially if you're writing like a thesis or a research paper, these could be because it combines different aspects into one figure, so it makes it a little bit appealing. We have those, we have those, we have those. Okay, yeah, exploratory. Let me jump into this one first before we continue, since we have it, because I don't think I have this in my slides. So we're gonna go over softwares, I think, in chapter 5 or chapter 6. But for now, this exploratory is like a free software you could use to do some machine learning plus some data analysis. And once you download that, we'll share the link with you, like once that chapter is there. Let me see, where's my, no, not this one. There we go. So I'm hoping you can see the exploratory. So exploratory is data science software, machine learning software. Once you add in the data, um, it basically shows you which are the specimens, the features that you'd like. You can opt to, not include those, or you could include them. This is the same Excel sheet we had for the example. So once you save it, let's say chapter 3 example. It plots everything. Let me see. Yeah. It plots histograms. It shows you the min, max, median, mean, standard deviation by default for all features. For instance, for categorical features, as you can see, we don't really have min, max and stuff. So if you go to Analytics tab, you could run correlation analysis. You could also run machine learning analysis. We'll come back to those when the chapter hits. But for the variables, it by default identifies the numerical variables. Categorical ones don't fall in because we're using linear correlation. And if you run it, there you go. You have the correlation between each different all the variables. This is, as you can see, it's all one. You could change the visuals a little bit from here. I believe you could also add show correlation values there, so you can have the correlation values. You can see further analysis significance scatter matrix. This is the one we had in the slide as well. And you can see the data. Shows you the highest correlation is between diameter and axial capacity, basically because you could fit a lot of concrete in a steel tube to get to capacity. So if you go back to filtering methods, this is actually a good example here. I didn't think about this before. But let's say we have all those features, 5 features or 6 features, and we want to filter them quickly to pick or to select a feature. It would make a lot of sense to select diameter here, since it has the highest correlation. Maybe diameter, tube thickness, because our Y is axial capacity, so we can use these two. As you can see here, we have compressive strength of concrete is negatively correlated with effective length. So the length of the column and the compressive strength, there isn't a lot of things going on there, so we may not be needing those, but these two are important. So this is how we can have this. You could Spearman, you could go for Spearman as well and apply. The numbers will change. So you could do Pearson or Spearman. Yeah, we could different other things. You want to remove these. Yeah, we can make this so we only have similar to Excel, the format to Excel. Uh, so this is the example we carried out here. You could also, you can see the plotting since if you go to the tab, to the, no, not to the chart tab, somebody could say, well, I want to have some histograms, and I want to have the diameter. So this is the diameter. You could also, uh, no, let's go back. Let's do scatter plot. This y would be, I don't know, number of rows, let's say without diameter. Let's go for this away. What I like about this is you could also add different colors. So you would say, well, now I have two axes, diameter and axial capacity, and the colors are the diameter. You could change this into yield strength of concrete. So you can have more information to show. You can also make this as well. I want the size to be the tube thickness. There you go. So you have axial capacity, diameter, and yield strength for color, and the size is tube thickness. You can have multiple things. You can also add, yeah. So this is what was this? Yeah, I don't think we had something. Let me see. I could also repeat this, so you can have different ones for different yield strength. You can have multiple figures. You can fit them. You don't have to fit them. Of course, I also think you could do this as 3D. Let's say commerce strength. We have a 3D. Yeah, it might take on. You could easily visualize. It's a very neat tool, visualizing things. I also know that you could change the coloring too. There's a lot of options that you can find. Yeah, we'll have a full chapter on these softwares, so you could mod multiple ones on the same figure. Yep, we've done this. Boxes, pies. Yep, we've done this Excel too. Yeah, I don't think we talked about this. So usually if you have up to 0.2 is weak, moderate between 4 and 6, 0.4 and 6, strong between 0.6 and 8, very strong between 0.8. This is for the correlation. Mutual information goes, I think, from 0 to infinity, so we don't really have it as easy as the correlation one. Yeah, we've done the correlation one. Here. Yeah, I remember here whenever we talk about correlation, remember the fundamental. Is it like linear? Is it mutual? Is it what kind of assumptions are based on these values? Yeah, we mentioned the redundancy thing. Some features are more relevant, some are redundant. Filters and normalization, standardization. Sometimes the standardization is called z-score normalization. Hmm. Yeah, let's see this. I think this is important. Let's see what 19 is. Yep. Okay. Comparatively, a machine learning model may deduce that a particular feature has little impact, if at all, on the target. So the machine learning will just remove that feature. This is if we're doing like embedded methods and stuff. So if you're doing this and the feature is actually physically important, then it becomes a problem. So because we're losing a lot of the information we need, even though it doesn't add much to the prediction. What's more important is this scenario. Let's say you have an engineer that they don't really have a lot of domain knowledge. They look at the machine learning and they see the model has removed one thing. And they say, well, if the accuracy is high, I don't have to use it because they don't know the physics behind it. So this becomes one of those cases where you might have a lot of issues because physically we need it, but the model has taken it out and we don't have justification to why we can remove it. Yeah, Google has 20 rules on machine learning. Um, you can Google this. This is actually very good to have, very good to read. Population of samples, central limit theorem, regression, the assumptions. You can see the notes are just massive here. Penn State has an online course, by the way, that goes through a lot of these things. I would advise you to go there and read a little bit. Oh yeah, this is a good example. So one of my colleagues, Eduardo, he was kind enough to let me share. So this is Eduardo in Spain to share a tool he developed for his course. He teaches. So let's say we have some data and we would like to fit a straight line. So you could if we can say I would like a straight line, a quadratic line, exponential line. And this is what we have. So if we have no reload. We were just doing fine. Let me come back to it. What's going on here? I don't like this one. Let me try. I think it might be something with my Wi-Fi. Let's see. Let's go back to the PDF. So it's like you could manipulate the slope and intercept, and for each one you can see the difference in error. So for instance, if you have the intercept is 0, slope is 0, this error is 163. If you modify it a little bit, you can see that the error is as reduced a little bit, which means that this is a better performance than the other one. Okay, we'll come back for it. And then if you change the slope more, you can see that the error reduces from 61, 42, 41. And then I think this is the least thing we could go for. The same process with Excel. Different versions. Yeah, whenever we go with polynomials, then you're gonna have to say x is strength, then x squared is strength square or strength cube. So how do we physically interpret these terms? What's strength square is? Logistic is where we try to have, let's say, binary analysis, yes or no, class 1, class 2 kind of thing. Very simple form. Blueprint, data statistics, problem. Okay, let me see that. Let me see if I can fix my Wi-Fi. Because I really would like I was going to show Eduardo's thing. One second. I don't know. I keep getting this. The server took too long to respond, so I'm thinking this like will updating the server or something. But if you want to see this, all what you have to do is this is the This is the book. So notes for predictive modeling. Um, this is by Eduardo. Here's the website. You can see that. And I believe if you go to 2.2 model formulation, and here you should see that script, the same image we had in the book, and you can manipulate that easily from there and try it a little bit. I'll try to revisit this and hopefully update this recording. Mm, he really has some good figures, and you have all the applications. Well, hopefully this was interesting. I know this has taken a little bit longer than anticipated, but this is a lengthy chapter, and hopefully we'll get to see you sometime soon. If you have any questions, please let me know. Best of luck, and hopefully um, everything works out well. Bye bye.